Okay, so this will be the second lecture out of chapter 1. So in the first lecture we talked about what matter is. So in this lecture we'll start talking about how do you make measurements on matter. So if you're going to make measurements on matter, then you need a unit, and scientists typically will use the SI system. So it's developed back in 1960. So in the SI system, there are what are known as base units. So there's 7 base units from which all other units are derived. So what are those base units? So for the length, the base unit is the meter. For mass, the base unit is the kilogram. Time, it's the second. And temperature, so most of you are familiar with probably 2 temperature scales, Fahrenheit and Celsius. In science, it's more common to use a temperature scale called kelvins. And so we'll talk a little bit more in another lecture about how to convert between Fahrenheit, Celsius, and kelvins. The amount of substance, so that's not how much something weighs, that's how many of them there are. Like if you had 10 pencils, the amount of substance in chemistry is the mole. And so given the abbreviation MOL, the electric current is the amp. And luminous intensity, so what does that mean? That basically means how bright something is. So luminous intensity is the candela. So they're the 7 base units, and all of their units are derived from these units. So some of these units are more commonly used in chemistry. So these 7 units, which do you think is not very heavily utilized in chemistry? Most chemists don't deal with luminous intensity too much. That would be something more of a physicist or electrical engineer might worry about. We don't have to deal with electric current too much, but there are some electricity, obviously batteries or chemical reactions. So if somebody dealing with electricity would deal with electric current, but most chemists don't have to deal with current too much, other than plugging something into a wall and using the electricity. But the other units, the other base units, chemists use all the time in chemistry. Okay, so what are derived units? So that would be something like area. So if you have a square, how do you calculate its area? Or a rectangle in this case, it would be length times width, right? So a distance times a distance, and a distance in the base unit is the meter, so that would be a meter times a meter. So a meter squared would be a derived unit from one of the 7 base units, in this case just length times length. So if you had a cube, how do you calculate the volume of a cube? So that would be length times width times height. So a distance times a distance times a distance. So a meter times a meter times a meter. So the volume would be in the SI base system unit, since it's a length is the meter, then the volume would be a meter cubed. But a meter cubed is not a convenient unit of volume in chemistry. Why not? Is because it's huge. A meter cubed is a huge volume. So 1 meter is about 3.28 feet. So if you had a cube that was 3.28 feet in length and width and height, so 3.28 cubed, that volume, so that would hold a volume of 264.17 gallons. So that's an absolutely huge volume. So in chemistry, a meter cubed is not a very convenient unit of volume. A more convenient unit of volume is a centimeter cube. So if you had a cube that was a centimeter times a centimeter times a centimeter, so 1 centimeter cubed, that cube would hold a volume of 1 milliliter. And obviously, a milliliter is a very convenient unit of volume in chemistry. So 2.54 centimeters is 1 inch. So if you had a cube that was about 1/3 of an inch, so 0.393 inches on each side, that cube would hold 1 milliliter of volume. Okay, so another common derived unit in chemistry is what's known as density. So what is density? It's a mass of the substance divided by the volume of the substance. So if you had a block of metal, for example, if you took the mass of that metal and you calculated the volume of that cube, then the mass divided by the volume would be its density. So in the SI unit, then mass is the kilogram. right? And the volume would be meter cubed. So kilogram and meter cubed. But again, this is not a convenient unit of density to a chemist. One, because a kilogram is a lot of material. That's a lot of mass, and a meter cubed is a lot of volume. So to a chemist, a more convenient unit of volume is grams per milliliter, or grams per centimeter cubed. So that's something you should just memorize. So when somebody says pair, for example, you probably think of 2. So when somebody says density, you should immediately think, you should learn to think like a chemist. Somebody says density, you should think grams per mil. Why? Because when you do calculations in this class, you have to keep track of units. That's how you get to an answer. That's how you set a problem up, is you set the problem up so that the units work out right. And so if you don't know the unit, then you can't do the calculation. So whenever somebody says density, what should just pop into the back of your mind is just grams per mil, so that when you can set the math up, right? So solids on Earth, on average, are about 1 gram per mil to about 22.5 grams per mil. So something that's really dense would be something like a neutron star, where its density is about 10 to the 15 gram per mil. Okay, so in the SI system, it's a decimal-based system. It's based on units of 10. So we'll look at several. So in the SI system, there are prefixes and then symbols associated with that. So we'll look at numbers, so from 10 to the 0, so that would be 1 of something. So for example, 1 gram or 1 liter or 1 penny. Or if you have 10 to the 1 power, so 10 of them, the prefix is deca and the symbol is DA. 10 to the squared, so that would be 100 of something, right? 10 to the squared. So if you had 100 of something, that would be equivalent to saying you had 1 hecto of it, and the symbol is H. So if you saw 1 Hg, that would mean 1 hectogram. That would mean you have 100 grams, right? So those two are not very commonly used. 10 to the third is used all the time. I'm sure you've heard of kilo before. So 10 to the third is 1,000, right? So 1,000 grams is the same thing as 1 kilogram. So the way to interpret this is that if you have 10 to the third of these, 10 to the third of something with no prefix, so 10 to the third, so 1,000 grams, that's equal to then 1 of these, 1 kilogram. Okay, so the others, so I filled in the ones that are not very commonly known. 10 to the 15 is peta, 10 to the 16, 10 to the 18 is exa. So after you get beyond kilo, then all of them are capitalized. So this would be a capital E and a capital P. So 10 to the 6 is pretty commonly known. So 10 to the 6 is mega. So that would be a capital M. So you could say 1 megagram, for example. So 10 to the 6 is a million. So if you have 1 million grams, you have 1 megagram, or 10 to the 6. If you have 10 to the 6 grams, then you have 1 megagram. 10 to the 9 is very commonly known. 10 to the 9 is giga. So capital G. So of course you hear of mega and giga in computer lingo, right? Gigabyte, megabyte. And 10 to the 12 is tera. And you hear of that in computer lingo as well, because you could have a terabyte hard drive, for example. So 10 to the 9 giga is a billion. And 10 to the 12 tera is 1 trillion. And that would be capital T. Okay, so if we go smaller, so to negative exponents, so 10 to the minus 1 would be 0.1, right? If you have 0.1 of something, the prefix is deci, and the symbol is little d, so all of these are not capitalized. It's only the ones 10 to the 6 and bigger that are capitalized. So 10 to the minus 2, so that would be equal to 0.01, so that would be 1/100th of something. So 100th of something is centi, little c. 10 to the minus 3 is 0.001, so that would be 1,000th of something, and that is milli, little m. 10 to the minus 6 is micro, and that's given this symbol. So that's the Greek symbol mu. So that would be 0.000001 of something. That would be a millionth of something. And 10 to the minus 9 is nano, given the symbol little n. So nano's pretty heavily utilized in today's language as well, if you've ever heard of nanotechnology. So that would be things that are really, really small. So 1 nanometer is about the size of 10 atoms stacked side by side. Okay, and then the others that are not very commonly known, 10 to the minus 12 is pico, 10 to the minus 15 is femto, and 10 to the minus 18 is atto. So, this SI system based on powers of 10 is very convenient because it's easy to do conversions so long as you know the exponent. So long as you know the prefix and you know the exponent, then it's extremely easy to convert between the different units. Okay, so let's take a few examples. So if you had 37,526 grams of something, then how many kilograms is that? So again, that's easy to know. So if it's wrote like this, grams, and there's no prefix, right? If there's nothing in front of the unit, then that means you're at 10 to the 0. And you want to go to kilo, so you want to go to 10 to the third. So 10 to the 0 versus 10 to the third, that's 3 powers of 10. So however many powers of 10 different it is, that's how many places you move the decimal point. So if you're going to be converting from a bigger unit, converting to a bigger unit, you're going to move the decimal point to the left, so the number has to get smaller. So in this case, we're moving from grams where there's no prefix, so we're moving from 10 to the 0. Right, so we're moving from here to 10 to the third, so we're moving to a bigger unit, so the number's got to get smaller, so the decimal point has to move to the left. If you're converting to a smaller unit, then the number's got to get bigger, so you have to move the decimal point to the right. Okay, so 37,526 grams, and we want to go to kilograms. So there's no decimal point explicitly written, but it would be understood that it's there, right? So we want to move it simply 1, 2, 3 places to the left. So that would be 37.526 kilograms. So again, if you know the prefix, and you know kilo is 10 to the third, for example, then that you know how many places to move the decimal point. So the conversion is trivial if you know that. So if we wanted to set this up mathematically and do the mathematical calculation, then again you have to know kilos 10 to the third. So since this number is on top, so we're going to set this up on a dimensional analysis, and we'll talk more about dimensional analysis in another lecture. So this gram is on top, so we need gram on bottom here so that they can cancel each other out. And then we would need kilograms on top, since that's what we're trying to convert to. So now where does the 10 to the third go? So this gets confusing to students because the 10 to the third is wrote in this table besides kilo, but what you have to keep in mind is what that means is that means there's 10 to the third of these in 1 kilogram is what that means. So basically you're taking 37,526 and dividing them by 1,000. So you get 37.526, right? Okay, so if we take another example, so how many nanoliters are in 0.0502 milliliters, right? So there's your prefix. So there's your unit, it's in liters, and there's your prefix is milli versus nano. So if you want to convert from milli to nano, so then you have to know milli's 10 to the minus 3, nano was 10 to the minus 6, and then look how many powers of 10 are between those two numbers. So there's 6 powers of 10 between the two numbers. So we want to move the decimal point 6 places. All right. Now, which way does the decimal point need to go? Well, we're going from a small unit to an even smaller unit. So the unit's getting smaller, so the decimal point has to move to the right, so the number has to get bigger. So we would simply take this and move the decimal point 6 places to the right. So 1, 2, 3, 4, and then 5, 6. So 2 zeros after that. So 50200 nanoliters, right, would be the answer. Or if you want to set this up mathematically, so the way that I do, so if we're at milliliters, I typically would convert from there back to here, back to 10 to the 0 power. And then I'll do, once I'm there, then I'll convert to there, back to the other one. It's just easier for me to think about it that way. You don't have to do it that way. That's just the way that I find it convenient to do this. So millis 10 to the minus 3. But then again, you have to keep in mind that 10 to the minus 3 goes with this. So there's 1 milliliter and 10 to the minus 3 liters in 1 milliliter. And now we only, so now milliliters cancel. So now the units would be liters, and we, am I doing this right? I feel like I'm doing this wrong. No, I'm doing this wrong. What's wrong with this? Okay. Did I do this wrong? We'll see. Okay, so there's 10 to the 9 nanoliters in 1 liter. That is, yes, okay, I'm doing this right. Okay, scared myself for a minute because I was going to be multiplying these numbers, and then I was thinking, oh, my number's going to be getting smaller, but then it's going to get bigger again when I multiply it by 10 to the 9. Right, so there's 10 to the 9, 10 to the positive 9 nanoliters in one liter, or that would be equivalent to saying there's 10 to the minus 9 nanoliters, no. Or that would be equivalent to saying there's 1 nanoliter is the same thing as 10 to the minus 9 liters. So it wouldn't matter what you use. You could put 1 here, and you could put 10 to the minus 9 here, and you're going to get the same answer, right? Okay, so if we do that, then you would get the same number, 50200 nanoliters. Or if we put that in scientific notation, so if the decimal point's there, let's move it back. So to write it in scientific notation, the decimal should go after the first, there should be one number and then a decimal point. So 5.0200 times 10 to the, we move the decimal point 1, 2, 3, 4 places. So 10 to the 4, so 5.02 times 5.0200 times 10 to the 4 nanoliters would be the answer. Okay, one more example. So how many kilograms are in 13,352 milligrams? So again, if you know that milli is 10 to the minus 3 and kilo is 10 to the positive 3, then how many powers of 10 is between those two numbers would be 6. So we have to move the decimal point. So 6 powers of 10, so we have to move the decimal point 6 places. Right now, which way does it have to go? So we're going from a small unit to a big unit. So the decimal point has to go to the left so that the number gets smaller. So we'll move it 6 places, so the decimal point is there. So 1, 2, 3, 4, 5, and then 1 0, so 0.0133352 kilograms. Or if we put that into scientific notation, then we would move the decimal point to, so that it is after the first digit, the first non-zero number. So 1.3352 times 10 to the, we move the decimal point to the right here, so this would have to be a negative exponent, right? So 1.3352 times 10 to the minus 2 kilograms. Okay, or again, if we did this mathematically, so since milligrams are on top, then we need milligrams here. And again, I always like to convert to where there's no prefix. So I would convert to grams, and then once I have it in grams, then I would convert grams to kilograms. And then you just have to know which number goes in front of each of these. So milli is 10 to the minus 3, right? So there's 10 to the minus 3 grams in 1 milligram. So you could do that, or you could do this. Or you could say there's 10 to the positive 3 milligrams. There's 1,000 milligrams in 1 gram. And then there's 1,000 grams in 1 kilogram. right? So you could do that, or you could say there's 1 gram and 10 to the minus 3 kilograms. The math is the same. So same here, right? You could say there's 10 to the minus 3 grams and 1 milligram. So it doesn't matter how you do it, you get the same answer, but you just have to know how to use those numbers. Okay, so if you do this, then you get 0.013352 kilograms. Okay, so hopefully that made sense. And again, so this is much easier to do than non-metric system conversions. For example, if you had 12,659 inches, well, how many yards is that? Well, that's not so easy to do unless you know the conversion factors. And you might say, well, you have to know conversion factors here, right? Which you do, because you have to know these powers, but that's all that you have to know. If you wanted to do these type of conversions, you need to know every single conversion factor. So how many gallons and pints is 614 cups, right? So whatever unit you're changing between, you have to know that conversion factor, whereas in the SI system, you only have to know these. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There's only 6 numbers to know. You have to know those 6 prefixes, and you can do any conversion that you want to do. Okay, so lastly in this lecture, so we're making measurements on matter. So if you're making measurements, and one thing you have to worry about is precision and accuracy. So precision is the closeness of a set of measurements to each other. So they may or may not be accurate. And accuracy is the closeness of one single measurement to its true value. So we try to illustrate this concept. So if you're playing golf, for example, and let's say you shoot 5 golf balls at 3 different holes, and if some of your shots, so your first 5 shots look like that, then how would you describe those shots in terms of precision and accuracy? Well, this would be not precise, right? There's no precision because they're all over the place. They're not close to each other, and they're not accurate because none of them are in the hole. So the goal is to get it into the hole, right? Or, so now you take 5 more shots, and if your 5 shots look like that, well, then now we would say this is precise, but not accurate. So it's precise because all of them are clustered together. So all of the measurements are close to each other, but it's not accurate because none of them are the actual value. None of them are in the hole. And then if you shoot 5 at this one and your shots look like this, then you would be both precise and accurate, right? They're all clustered together and they're all in the hole. So if we take an example from chemistry, so let's say you want to do a reaction and it needs 6.3 grams of potassium bromide. And so you're working in a research lab, and we have 4 different, so maybe it's a teaching lab, and we have 4 different groups that are doing this experiment. So how would you go about getting the 6.23 grams? So you would go to a balance, and you would put your beaker on it, and then how do you zero it out? What is that called? So there's a button here that you would push, and that's called tar in the balance. So you put your beaker on and then push the tar button, and that would zero it out so that it reads 0 grams. And then you would start adding the potassium bromide to the flask, right? And then when you get close to your 6.3 grams, as close as you can get, then you would stop. So 4 groups make this measurement. One group gets 6.25 grams, one gets 6.24, 6.23, and 6.25. So would you say those measurements are precise? And that's a tough question, I guess. So I guess it means how close do they need to be to each other for things to work, right? So that's kind of an abstract question, whether it's precise or not, but these are all clustered pretty close to each other, so we'll just say that they're precise. And now the question is, are they accurate? Well, I mean, group number 3's got it right on, right? 6.23 grams is exactly what you need. So we would say that would be accurate. But then how do you know? How do you really know if it's accurate? How do you know if there's actually 6.23 grams in the balance? And so would you say just because that's what the number says 6.23 or 6.25 in this case, so that's what it is? So how do you know? How do you know it's not really 10 grams and your balance is just off? So that would be something a scientist, engineer, anyone making a measurement has to know, right? You're using a device or a piece of equipment to make a measurement. How do you know if the piece of equipment is actually giving you actual true values? So how would you do that if this was a balance? How would you know if the balance is actually reporting something that's the correct mass? Well, one way that you could do that is you would need to calibrate the instrument. So in case of a balance, what you would do, for example, take something that has a known mass. So the manufacturers of that balance may send you a platinum block or some block that is a mass that is known to several decimal places. So you would put that block on the balance and weigh it. And if your balance is off, then you have to adjust the balance and tweak it until it reads the right mass, and then your balance is calibrated. And so now you can be confident when you measure other stuff that it's going to be reporting the right mass. So that would be anytime you work with any instrument and making measurements, you always have to be concerned with, do you know that your instrument is correct or not? That it displays results accurately or not? Okay, we'll stop there.